Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the nanoHUB-U course, Thermal Energy at the Nanoscale. I'm Tim Fisher from Purdue, and this week we're going to talk about thermal properties, and today I'm going to give you an introduction of the idea of specific heat. We're going to start looking at what we'll call internal energy, which is generally the sum of all of the energies, all of the degrees of freedom, kinetic energy, vibrational energy, electronic energy, that is available in the microstates that we talked about in last week's lectures. And we'll kind of separate two different concepts. One would be phonons or lattice vibrations from the electronic part, because the forms of the results are a little bit different. We'll put them together at the end. So we're interested in the energy of a quantum particle, and then we're going to multiply that by the number of those particles with that energy. So that's our distribution function. At least the average occupation was our distribution function. And when we take that product, then we have to sum over all of those different types of carriers. So that's what we're showing here. It gets a little bit cumbersome. I want to point out a couple of things. First of all, capital U is the extensive internal energy. So that means that it depends on the size of the system. So we'll make it intensive in a moment, meaning that it shouldn't change with the size of the entity under study. These two summations, the first one is the summation over K, and that's a bold K. It's a subtlety, but what I mean by that is that we're summing over all of K space in any of its dimensions. Right? We're going to try to keep it as generic as possible so that our results could apply to 1 dimension or 2 dimensions or 3 dimensions. So that's why the bold K is there. And then P is a sum over branches, or sometimes it's called polarization. So for phonons, we've already talked a little bit about different kinds of polarizations, acoustic and optical. There's some more that we'll talk about as the course progresses. And then we have this energy term, and generally speaking for phonons we convert that to frequency, so that's h bar omega. And then we have our distribution function, and we're trying to keep things as generic as we can. So the subscripts I mean that we're going to be generic now, and then we would apply the right kind of statistics through that subscript I. And I'll just note one thing that we've done here is we've neglected the 0 point term, which we talked about a little bit before. And the reason that we do that is that the 0 point energy is really not thermal energy per se. It doesn't depend on temperature. It's a constant times the quantum energy E. And so we're just going to leave it at that and keep it out of the analysis from here on. For most of what we do, it won't matter because we'll be taking derivatives of the total energy with respect to temperature, and because the 0 point energy does not depend on temperature, it doesn't really factor into our properties. So this distribution function, I just wanted to touch on it again. The distribution function is a synonym for the average occupation number, and that's what depends on temperature. In fact, in much of what we'll do, that's the only thing that depends on temperature. So you see this, again, this distribution function here for different kinds of statistics. Fermi-Dirac applies to electrons or fermions more generally, and then Bose-Einstein statistics apply to phonons and photons, and we call those sometimes bosons. And lastly, Maxwell-Boltzmann statistics, which is sort of a limiting semi-classical form that often is used for the analysis of gases. So again, this is the important function. We're going to take its derivative with respect to energy and with respect to temperature, and so this is the thing we'll have to manipulate quite a bit mathematically as we go forward. The other difficulty that often arises is this K-space summation is challenging, it's cumbersome, and it's sometimes not easy to do analytically, or we make some approximations about the K-space so that we can do an analytic evaluation of the integral. And this identity that I show here, where f is a generic function, we can either sum that over all of k-space, and in this, what we're doing here is we're normalizing by the volume. That's L to the power d, where d is the dimensionality of the system. That summation can be converted to an integral over k-space divided by 2 pi to that same power d. And if 2 pi raised to the power d and L raised to the power d looks a little bit familiar, that's because essentially that comes from the spacing of allowable states in k-space. Okay, and we put them on different sides of the equation here just to make this normalize, because what we're going to do a lot of times is we'll divide our problems by the volume, and volume is in quotes, that's L to the power d, so that we can have a property or an answer that does not depend on the scale of the system. It might depend on the dimensionality, but not the scale of the system. So this specific internal energy, so this is, if you studied thermodynamics, you've heard this word specific, and what it means is it's normalized usually by mass, just so that for those of you who've seen it before. In this course, we're going to normalize it by volume instead. It makes it just a little bit easier. The math kind of comes out a little bit easier, and of course we can convert between a volume and a mass basis simply by including the factor of density, mass density. So if we go through that's what this L sub d is, and I'm going to, or L raised to the power d rather. This is what we're going to call volume. Almost no matter what dimensionality we're looking at, we'll call that volume, where d, again, is the dimensionality of the problem. So in 3D, that's L to the power 3, where L is some characteristic length of the overall system of interest. But in 2 dimensions, our volume will actually be an area, L to the power 2. And in 1 dimension, it's a length. So now getting to the specific heat, we have the definition. This is the fundamental definition of specific heat. It's the amount of thermal energy per unit something, per unit mass or volume, required to raise that entity's temperature by 1 degree. So another way, that's usually the way we teach it. We can get the same thing by just saying it's the derivative of internal energy or specific internal energy with respect to temperature. Now, we said before that the only thing in the internal energy expression that depends on temperature is the distribution function. So we can just make that, we only need to differentiate that one part of the integral or summation. And we're showing here now underneath the main equation, the definition equation for specific heat, we're showing that that temperature derivative of the distribution function explicitly. And it's not all that complicated. We actually, by differentiating with respect to temperature, we find that we have the distribution function again, but it's squared, and then multiplied by an exponential term, and then a term that shows the ratio of energy, of particle energy or carrier energy to thermal energy divided by temperature. So if you wanted to do a unit or dimensional analysis on this, you see everything in the equation is dimensionless until we get to this last t, right? If we think of energy divided by kT, that's dimensionless, and then we have an extra temperature here, and so this has the proper units of 1 divided by temperature. Now I said before that these k-space integrals can be very, very messy, and what we'd like to do most of the time is to convert them to an easier space. That's energy space for electrons usually, and frequency space for phonons. And you'll have plenty of examples to do through homework. I just wanted to show you a couple of things for our purposes here. One of the things that's often done, but maybe not explained all the time, is that if we have an integral, I'm going to draw it here. We have some integral of, let's say, a function g, and we're integrating over in k-space. So let's say that it's 2 or 3 dimensions, so I'm putting a vector over the k. If you want to put that in Cartesian coordinates, that means that it's dkx, dky, dkc, so it's dkz. It's a multi-dimensional integral. That would be in 3 dimensions. But let's say I had a 2-dimensional problem. What we can do, if we make some assumptions about symmetry in the k-space, And we will do that often, even without a whole lot of justification. So if we had 2D, this integral, which I'm going to call up here, I'm just going to call this I, we will write it in radial coordinates instead of in that Cartesian coordinate. So this integral, I, we will write as the integral of g, and then a two-dimensional integral in radial coordinates, we will write it as 2 pi, the circumference of a circle in k space. So let's say I'm doing this in phonon space, so that's capital K. 2 pi k dk, where k, this is a capital K, is defined as the magnitude of the k vector. So that what that means is it's really serving the function of the radius in k space. Okay, and similarly, in 3 dimensions, we do this. This integral will be, again, this g term, which depends on k, so we'll keep it there. G depends on k, and so then this will be the surface area of a sphere with radius in k space, capital K, squared, integrated over dk. All right, and so we'll use that a lot, and we won't always say we've done it, but there's a big assumption in this, and that is, of course, that g depends only on the magnitude of the wave vector k, not a specific direction or in radial coordinates some angle. Okay, and that's it's a very common thing that's done. We'll need to do that to get closed form answers, and you'll see that coming up very soon in the next sequence of lectures. That's it for today. Thanks.